What we're going to look at in this lesson is what are called Maclaurin polynomials, and as you see here, Maclaurin polynomials are used for estimating the value of other functions by making a polynomial that resembles the function. So we're going to look at other functions and try to find polynomials that look a lot like those functions. It won't be across the whole domain, but across the domain that we're going to be interested with. So again, a Maclaurin polynomial is going to represent another type of function. So we're going to make exponential functions and trig functions. We're going to find polynomial functions that look like those functions. Now, we can kind of talk through this first part and see where it comes from or where the first ideas come from. And then we're just going to continue those kind of indefinitely. So here's what we do. The first thing we're going to do is we're going to pick an anchor point around which to bend the polynomial to make it fit. And the nicest anchor point is when x equals 0. So here is a function here. We don't know what it is. It kind of looks like a polynomial, but it might be some other function. So what we do is we really just pick an anchor point. And our anchor point in this case, and the easiest one, is when x is equal to 0. The next thing we're going to do is we're going to approximate this function as a horizontal line. So this horizontal line is, we're thinking, okay, this is my polynomial that looks like this. Now, if we think honestly with ourselves, this polynomial looks nothing like this function right now, but it is a start. So, and even if you think about this, in this area here, our polynomial, maybe a little smaller, our horizontal polynomial is a pretty good estimate of our function here that we're trying to estimate. So it's just a horizontal line. That's our first guess. So like just f of x equals maybe 2 is our first guess. So that's the second thing we do. We start by picking an anchor point about which we want to estimate. Then we make a horizontal line, and that's saying that's our first guess. Well, we can make that guess better. We can make a line that resembles this a little bit more. So what we do now is we come up with a linear, something other than a horizontal line, but still a line. So now, this being our Maclaurin polynomial, kind of, we're not there yet, but we're getting closer. So this line maybe is a fairly good guess of this function in this circled part. So how do we find, or how do we get the same slope? Like this is a tangent line at this point. Well, that has to do with the derivative. And so we're going to end up taking the derivative to help us find an estimating polynomial called a Maclaurin polynomial. Well, this line is straight, obviously. We don't want it to be straight. Can we do something with the curvature? Well, that has to do with concavity, and we know that second derivative has to do with concavity. And so we're going to look at concavity, and we're going to try to curve this the same as our function. So now we have an even greater area that our Maclaurin is pretty close to this function, and maybe even it goes further where it's not that far off. And so that's the idea behind a Maclaurin polynomial, is we take our horizontal line guess, then we change the slope so it looks a little more like it, then we change the concavity. And number 5, that we don't have an easily describable geometric meaning to attach other derivatives, the process continues. So the more the derivatives you work with, the better your estimate will be on your polynomial. So here's what we're going to do. This is really a process that we're going to work through, and we're going to use this right here. Our Maclaurin polynomial is going to be in this form. It's a polynomial, so and this is actually in ascending order rather than descending order, but this is our highest exponent, x to the n, and then x to the n minus 1, and we can work our way down. And so our polynomial will look like this, and then these a sub n's are defined down here, and it follows a pattern. So a sub 0, that constant is really, you plug 0 into your function over 0 factorial. A sub 1, which goes along your x with your x the first term, is the derivative at 0 over 1 factorial. A sub 2 is the second derivative. Plug in 0 and put that over 2 factorial. And so when you see this notation, this f to the n of 0, then that notation means the nth derivative of f evaluated at 0. So if there was a f with a little 7 up here, maybe that would be the 7th derivative. Plug 0 into it. So we are going to just follow this process and do this several times just so you get the hang of it. It is a process. It will take you some time at first to remember these different things, but once you get good at it and get some practice at it, it won't take very long. It does help to fill out a table too when you go through this, and so we'll be doing that. So here's our first one. Find the Maclaurin polynomial for f of x equals 2x squared plus 3x minus 4. Well, I did bring this, I have this here to help us remember what to do here. We're going to come up with a polynomial, and it's going to be in this form. And really, the x's are easy. It's x to the 0, x to the first, x squared, x cubed, and you keep working your way up. It's the a values that change. So what we're going to do here is we're going to do our derivative, and then we're going to plug in 0. So f to the n of x, and we're going to figure out what's f to the n of 0, and maybe we'll extend this and do the whole thing, f, the nth derivative of f evaluated at 0 over n factorial, and that will actually give us our value. So the first one, a sub 0, we just plug 0 into the function. So here's our function, and we're just going to plug 0 in. That's how we get our first one. So we might even make another column over here that just says n. So n is 0. We're not taking the derivative at all, and so it's still just the 2x squared. This might be hard to fit in here. 2x squared plus 3x minus 4. Sorry about that. Actually, we want to take the derivative of it, so we don't need to put all of that. Oh, no, we don't want the derivative. So we're going to put 0 in. If we put 0 in, 0 squared, so this is just negative 4. And we have negative 4 over 0 factorial. If you remember, 0 factorial is defined as 1. That's the only one that's a little bit confusing. So we get negative 4. And so this is our a sub 0. Now we're going to put in a 1. So this means we want to take the first derivative. First derivative of this is 4x plus 3. 4x plus 3. We're going to put in 0. So 4 times 0 plus 3 gives us 3. And so now we want to do 3, that 3 that we just got, over 1 factorial. Well, 1 factorial is just 1, so we get 3, and that is our a sub 1. Now we're going to do the second derivative, and it's going to be 2. The derivative of 4x plus 3 is just 4. So what is f of 0? Well, it's just 4. Because the second derivative is 4, so whatever x value you put in, you get 4. And then we're going to do 4 over 2 factorial, because our factorial keeps going up. And that's 4 over 4, which is 1, which is our a sub 2. We're going to take the third derivative. The derivative of 4 is 0. So this is 0, and this is 0 over 3 factorial, which is 0. And we'll actually see when we do the fourth derivative, derivative of 0 is still 0. So all of these are just going to keep being 0. So what does that mean? Let's see what that looks like for us. So our Maclaurin polynomial is f of x equals a sub 0. Well, a sub 0 is negative 4 plus a sub 1 times x, a sub 1 times x is 3x, plus a sub 2 times x squared, so 1x squared, plus a sub 3, which was 0, 0x cubed, 0x to the fourth. So this is it right here. This is our Maclaurin polynomial. In fact, sometimes I'll put m of x, so we remember this is our estimating polynomial. Now, if we take a look at that, that is the exact same function as this, which maybe you would have realized that happened, maybe not. But if you try to estimate or find a Maclaurin polynomial of a polynomial, it's actually going to be that polynomial. But again, we do this sometimes just for practice, so we get the idea of it. And so anytime you find the Maclaurin polynomial of a polynomial, it will just be itself. And remember, Maclaurin polynomial is really an estimating polynomial. So let's go to something different. This says find the Maclaurin polynomial of degree 4 for f of x equals e to the x. So what we're going to do here, we're going to make a table. We'll bring that out later. I'll bring this out because this will help us remember what to do. You will need to know this stuff in the future, so make sure you're getting used to knowing it. And so what we're going to do is we'll make a table here. We might condense our table a little bit to where here's our n, and maybe here's our nth derivative. I mean, we can go through and do the whole thing. The nth derivative evaluated at 0, and then that nth derivative over n factorial. So n is 0, which means we don't take a derivative at all. So we don't take a derivative, it's just e to the x, and we're going to evaluate that at 0. So e to the 0 is 1, and then we're going to do that 1 over 0 factorial. The definition of 0 factorial is just 1, and so we have 1 over 1, which is 1, and that is our a sub 0. Now we're going to plug in, or we're going to do n is 1, so our first derivative of e to the x is e to the x. And we do that derivative to the 0, which is 1, but now we do 1 over 1 factorial, which still actually turns out to be 1 over 1, which is 1, which is a sub 1. Now we might think it's always 1, but hopefully you realize as the factorials grow, this is going to change. Now we're going out to degree 4. So degree 0, degree 1, degree 2, degree 3, degree 4. So actually we're going to do this 1, 2, 3, 4, and 5 times. So we're going to go up to a 4 here. So we're going to do a 2, a 3, and a 4. And derivative again, it's nice and easy. Plug in 0, you get 1. So now you're going to do 1 over 2 factorial, which is 1/4. That's our a sub 2. Derivative is of e to the x is e to the x. We get a 1 again, which is 1 over 3 factorial. 3 times 2. 2 factorial is just 2. I don't know why I have 4. 2. 3 factorial is 6. And then derivative of e to the x is e to the x. So this is our fourth derivative. Plug in 0. You get 1. 1 over 4 factorial. 4 factorial is 24. And that is a sub 4. So now we can write our polynomial. I think I can fit it in down here. Our polynomial, let's write m of x for Maclaurin. This is our estimating Maclaurin polynomial. Is a sub 0, which we know is 1, plus a sub 1 times x, so a sub 1 was 1, so x plus a sub 2 times x squared. A sub 2 was 1 half, so 1 half x squared plus a sub 3 times x cubed. A sub 3 was 1/6. And then as we continue, our a sub 4 was 1/24 x to the 4th. And so that is the Maclaurin polynomial of 4th degree, degree 4, for e to the x. And that's all you do. If you wanted to, you could put it in descending order. So here, let's see if I can move this all the way over. Here, this is the graph of what we just did. And so you can see here is the real e to the x, and then our guessing polynomial, our Maclaurin polynomial, which gets close. So it's close all in this area. Obviously, e to the x gets closer and closer to the x-axis. This is to the 4th power, so it moves its way up. But it's a pretty good estimate in this area. So if we went higher than degree 4, our Maclaurin polynomial would get even closer and closer to being exact. Here's just a couple things back to what we were just working with. Here, if we did the same one, this is still e to the x. If we went up to the degree 7, it would look like this, and look how accurate this is. So here's our Maclaurin polynomial with the smaller arrow here compared to e to the x, and that is really close all the way in this area. So that shows that it's closer and closer. Now, as we continue this, e to the x, and also some other ones you can do this with, you can actually make a summation, because you're just adding up a bunch of things, and if there's a pattern here, we can write it as a summation. So they're using q of x, so we could be even more accurate and realize, what are we doing each time? Well, our first one was x to the 0, like this is x to the first, well, x to the 0 over 0 factorial. This is x to the first over 1 factorial. This is x squared over 2 factorial. X cubed, you really see it here, x cubed over 3 factorial, x to the 4th, and we can continue this indefinitely. We can keep going and going and going and going. And so what we can do is we can write this as a summation, because there's a pattern here. We can go from, let's use n equals, our first n is 0, so 0 to infinity, of x to the n over n factorial. This right here is the same as f of x equals e to the x. And that's what we have over here. And so we could go on forever and make a function that ends up being equal to that if we say the limit approaches infinity or something. Scratch that. So that is e to the x, a Maclaurin polynomial for e to the x. Here's up to the 7th, and here is actually up to infinity. Our last one, this is another nice one. This says go to degree 6. We could end up doing this the same way we did, or similar to what we did before. We could find a pattern, and we could go make a summation notation for it. So we're going to do cosine of x. I'll bring this out here again, although hopefully you're getting used to what this is. So what we're going to do is we're going to take our n, and that's going to be our different derivatives. It's going to be our nth derivative. We'll plug in 0. and then we'll divide that by the factorial that's necessary. And that will be, this will really be our a sub n. So maybe I won't write equals a sub 0, a sub 1, a sub 2. So we're going to go all the way down to 6 here because we asked for degree 6, 0, 1, 2, 3, 4, 5, and 6. And hopefully you'll see a pattern. Because what we're going to be doing is we're going to take derivative of cosine. And we've done this before where we took the first derivative second, and it keeps repeating because you go from cosine to sine and to cosine. I know the signs change. But so we're going to take our first without taking the derivative, which is just cosine of x. The cosine of 0 is 1. And so we want 1 over 0 factorial, which is 1. Derivative of cosine is negative sine. So we're going to do negative sine of 0. Well, actually, that doesn't make a big difference. Sine of 0 is 0. Negative 0 is still 0. So we'll have 0 over 1 factorial, which is 0. Derivative of negative sine is negative cosine. Negative cosine of 0 is going to be negative 1. And so we have negative 1 over 2 factorial, which is negative 1/2. Derivative of negative cosine is positive sine. Sine of 0 is just 0. So we have 0 over 3 factorial, which is just 0. Derivative of sine is cosine. Cosine of 0 is 0. So we have, is 1. That is incorrect. So 1 over 4 factorial. And that's 1 over 24. Now actually, if you look at this, here's cosine of x and here's cosine of x. So we actually went full circle. Derivative of cosine is 0, so we had a 1 there. And so these numbers are going to repeat. We had 1, 0, negative 1, 0, 1, 0, negative 1, 0. So it keeps repeating because of what happens with the derivative of sine and cosine. Derivative of cosine is negative sine. So negative sine of 0 is still just 0. And we get 0 over 5 factorial, which is just 0. And then derivative of negative sine is negative cosine. And negative cosine of 0 is negative 1, which gives us negative 1 over 6 factorial, which is negative 1 over 720. And so we have up to degree 6, and so now we can write our Maclaurin polynomial. It's a sub 0, which is 1, plus 0x minus 1/2 x squared plus 0x cubed plus 1/24 x to the 4th plus 0x to the 5th minus 1 over 720 x to the 6th. Obviously we can write this better because we have several zeros here. So this is actually 1 minus 1/2 x squared plus 1/24 x cubed. Ran out of room, so minus 1/720. Sorry, this is not a cube, this is to a fourth. X to the sixth. And so there's the polynomial of degree 6 that would estimate that. I'm going to go ahead and add a slide here, and we're going to look at that a little bit closer. So we saw that our Maclaurin polynomial for cosine was 1 minus 1/2, so minus 1/2 x squared plus 1/24 x to the fourth minus 1/720 x to the sixth. And this would have continued. There's a pattern here where positive, negative, positive, negative, positive, negative. And then what was going on here? Well, if we think back, this is actually, they're all ones in the numerator, so 1 over 0 factorial x to the 0, that's this one right here, minus, this was 2 factorial, 4, 6, and so we're going to have 1 over 8 factorial. You could figure that out, but x to the 8th minus 1 over 10 factorial x to the 10th. And this could continue on. We can write this as a summation. You end up having zeros in there, so that doesn't hurt us to put it in there. Let's see if we can think through this. We're going to have a summation, and we want to start at 0, and we can go up to infinity, which is fine. These are going to be fractions, and there's going to be factorials in the denominator, and there's going to be things to a power in the numerator. And the signs keep changing. So let's first deal with the square, the fourth, the sixth, the eighth. And notice those are the same, like the 8 and the 8, the 10 and the 10. Those are the same. So the way that we can, these are all even numbers. The way that we can get an even number is by multiplying something by 2. 2n, we don't necessarily want a 2n, because if we put 0 in here, well, let's work through it. So we can say x to the 2n. So if we put 0 in here, that gives us 2 times 0 is 0, x to the 0 is 0. Putting 1 in here gets us a squared. And so actually we can put a 2 to the 2n in here also, because that will get us the same factorial. So this always gives us an even number, which is what we want. Well, how do we change the sign? Well, in order to change a sign, all you need to do is multiply by -1. But -1, but we don't always want this to be negative. We want it to alternate negative, positive. So if we put a -1 here, -1 times any of these numbers is always a -1. So how do we alternate that? Well, we can do -1 times 2n minus 1. And what this does, if you put a 0 in here, you get 1. Actually, let's put a +1. If we put a 0 in here, you get a 2 times 0 is 0 plus 1 is 1. So -1 to the first, which is -1. If you put actually, we can just put an n in here, I believe, because if you put a 0 in, -1 to the 0 power is just 1, which we want when n equals 0, we want it to be 1. We want the next one to be negative, so when we put a 1 in here, that will be -1 to the first, which is -1. -1 times something will give us the negative. When you put a squared, -1 squared is 1, and so that gives you a positive. And so this part right here will take care of those alternating signs. So this is a Maclaurin polynomial, an infinite one. So that gives you for cosine, if you were to graph this, well actually if you were to graph this one, this will get you really close to cosine for a while, but then it would start to be inaccurate after a while. So cosine we know looks like this, and so our Maclaurin polynomial will look like that for a while, but then at some time it's a polynomial, so it's probably going to keep going up forever and ever, but it will estimate it well for a while. And that's Maclaurin polynomials. Again, they take practice. Once you get used to it, you get better at it, and we'll even be looking at these where we can write a summation to find those polynomials.